Thank you, Vilna. In my second presentation today, we'll discuss the things that they did not teach you about magnetic separators. In our contents, we'll discuss the duty of the magnetic separator in the dense medium separation plant. We'll also discuss the ideal operating conditions, in other words, the factors that affect our MagSep's performance. Then we'll push the boundaries in terms of those performances, and I'll list the figures where the MagSep starts to lose operational efficiency. Finally, we'll keep a case study entitled Keep on Driving Even When the Wheels Have Come Off. The most apparent duty of the MagSep is, of course, medium recovery. That is what we expect, particularly given the prices of correct medium powder in the industry. However, that is not the only function of a wet drum magnetic separator in our dense medium separation plant. Its other functions are, because the MagSep is an integral part of the DMS performance, the MagSep must provide an overt dense medium stream that allows easy control of the correct medium. In other words, the density discharge from our wet drum MagSep must be higher than the density of our correct medium. The difference between the two can then easily be altered by adding process water to bring the correct medium density up to design and operational specification. We also need to purge any non-magnetic fines from the circulating medium through the magnetic separator. We must bleed off degraded medium particles in circulation that can also go to tailings. This is important to regulate the viscosity of our correct medium. And finally, we can provide a degrit water stream that is free of coarse particulate solids that can be reused in our drain and rinse screen to save the overall water utility of the plant. In this diagram, we see a cross-section of a typical magnetic separator. On the right-hand side, we have the feed pipe feeding into the underpan or tank. We also see the rotating magnetic drum, the stationary magnets on the inside of the drum, and we see two effluents on the opposite side to the feed end. The first one is called the underflow, and this is where non-magnetics will report to. Over a fairly tall weir, as an optional extra, we can then add an overflow box that will have degrit water. The coarse and heavy silica particles will typically report to the underflow of the machine, with a fairly clean stream of water reporting into the overflow box. In the operation of the machine, the degrit water can be used and can be recycled back to the drain and rinse screen to rinse off any medium from our ore particles, and then that water would return to our dilute medium circuit, which in turn is pumped back to the MagSep. A second important operational parameter and function of the MagSep is to purge any non-magnetic fines into the underflow of the machine. A third one is to have a significant overdense product from the MagSep. We can see that the angle of the magnet is very important to ensure that the medium that is recovered is discharged over the lip of the MagSep and recycled back to the correct medium. The typical densities of these streams is 2.8 for magnetite and 3.2 for ferrosilicon on a dimensionless SG basis. Finally, we must also bleed out any degraded medium particles, which are magnetic, but because of the constant circulation within the correct medium, those particles can break down and decrease in size, which can add to viscosity problems over time. From the flow sheet we've already seen today, we can see the position of the magnetic separator relative to the other major equipment within a dense medium separation plant. In our first application, by employing an optional overflow box, we can have a product stream that is free of any large non-magnetic grit particles. That degrit water then is of good enough quality to be recycled back to the rinse portion on our drain and rinse screen to wash the medium off of the cyclone separated ore. In the second application, I'm postulating an effect where the MagSep is not washing out the non-magnetic fines from our circuit. In other words, we entrap a lot of non-magnetic fines onto our wet drum MagSep surface, which then from the MagSep reports back to the circulating medium sump. The circulating medium in turn is pumped through the mixing box and up to the cyclone where it separates. The cyclone underflow and cyclone overflow then reports to the drain and rinse screen. A lot of the fine non-magnetic material will report back into the correct medium, but also a significant portion of it might be carried over to the drain and rinse screen. At this point, those non-magnetic particles are washed into our dilute medium, which is fed to the MagSep. It is evident that if the MagSep do not get rid of these non-magnetic particles, they will forever stay in suspension and circulation in our correct medium, and it is therefore a vitally important role for the MagSep to get rid of these non-magnetic material, and it does not stay in circulation in the correct medium where it will cause viscosity problems in the operation of our plant. Our overdense is the next important parameter, where the overdense is directly returned back to the circulating medium sump. If the overdense density is higher than the correct medium density, we can control the set point density of our correct medium by adding processed water and measuring the density on line. If the density from our MagSep is too low, we may have to employ additional pieces of equipment with capital and running costs in the form of densifiers to assist with density control within our plant. Finally, as medium particles degrade over time, we also need to bleed off the ultrafines to tailings via the magnetic separators underflow and through to the tailings dam. This is again very important in terms of medium viscosity of our correct medium. The conclusions from our discussion so far and the positioning of the MagSep within the dense medium separation plant means that the MagSep does not only recover medium, but goes on to regulate the viscosity and the density, both of which are critical parameters to our cyclone performance. The MagSep is therefore an integral part to the dense medium separation health and performance. The MagSep serves as a kidney loop of purging spent medium, non-magnetic fines, water recovery, and ensuring operational density. An equation for that does not exist, but if we had to write one, it would probably look something like the equation at the bottom of the slide, where the dense medium separation health and performance is equal to the integral MagSep, and that MagSep in turn has to perform from its mechanical design all the way through to its process performance, denoting the limits of our integral range. Next up, the ideal operating conditions of a wet drum magnetic separator. The factors affecting its performance are listed here in decreasing order of importance, which means the slurry level in the machine, indicated by the red line on the cross-sectional MagSep in the top right-hand corner, is the most important parameter that ensures effective magnetic separation performance. The low-intensity magnets we use in these MagSeps are not strong enough to attract the medium through an air gap. The water, therefore, acts as the carrier medium so that when the magnets act upon our magnetic medium particles, they can be suspended in the water and be transported onto the drum surface from where they are recovered. The second most important parameter is the magnet angle within our MagSep. If the magnet shaft support is hanging freely at the 6 o'clock position, the magnet tip will not be high enough for the recovered medium to be discharged over the discharge lip of the MagSep. Very quickly, the magnetic circuit will be overloaded with a dense medium material that is recovered, And if there's no way to get rid of that dense medium, the magnetic circuit will become overloaded and the magnetic material will report to tailings, indicating significant losses of our medium and poor recoveries. The third most important factor is that magseps can be overloaded. We can feed slurry at too high flow rates, and the recommendation for a 900 millimeter wet drum magnetic separator is between 90 to 120 cubic meters per hour of total slurry for every meter of drum width. It may happen that a complete machine can be overfed. Or the second scenario is that we can have sectional overfeeding resulting from blocked pipes. Or the machine cannot be installed according to a spirit level, in which case deviation in the vertical and the horizontal plane would make a difference to the performance of the magsep. Finally, we could have surging flow into the machine, where occasional overloading would result in losses. Next up, the magnetic solids feed concentration. If that is outside of the recommended range of 120 to 250 grams per liter, we can expect recovery losses from our magsep. Second last, if we feed too much non-magnetic material into our magsep, we could also have losses. The value there is 25% non-magnetic material by mass over the mass of total solids fed into the machine. And lastly, our machine setup at critical dimensions could also affect its performance. We can further take the list from the previous slide and we can categorize the performance of the magsep into mechanical adjusted parameters or process parameters. Slurry level in the machine, magnet angle, overfeeding and machine setup are all mechanical parameters that can easily be adjusted on the machine in plant and safely during plant operation. However, process parameters are more difficult to control because often the magsep has to play second fiddle to certain operational considerations like correct medium density, cyclone feed rates, and also the amount of wash water required on our drain and rinse screens. Therefore, we have to keep a close eye on the process performance of our magsep, of which we often do not have control. Pushing the boundaries of the magsep efficiency, we first have to focus on the magnetic flocculation effect. The magnetic flocculation effect occurs when the contribution of magnetic solids in the feed to the magsep is between 120 to 250 grams of medium per liter of total slurry. In an externally applied magnetic field, ferromagnetic particles become magnets themselves. If the concentration of magnetic particles is high enough and the particles are close enough to each other, they will start to attract each other and they will form long chains, very similar to the phenomenon that occurs if you put a magnet into a bunch of paper clips. If you lift the magnet up, the paper clips will form long chains head end to tail end because they themselves become magnetized. In our magnetic flocculation effect, the first important step is that particles must be at the right concentration and close enough to each other to adhere to each other and form chains. The next step is that these chains start to interlink and intertwine. It is then much easier to recover the chains as aggregate particle volumes instead of recovering single particles by themselves. Too low a magnetic solids concentration does not allow these aggregates to form and starts to result in recovery efficiency losses as depicted on the graph on the right. The next important parameter is the percentage of non-magnetic material in the feed. Here we can see that there is evident a threshold value between 20 and 30% non-magnetic material in the feed. If we operate the magsep beyond that point, where we contaminate the feed material with more non-magnetic material, we start to see recovery efficiency losses, and if we have only 5% magnetic magnetite in the feed, we could expect recoveries as low as 87%. The mechanism that is at play here is that the non-magnetic particles break the chains that is formed by the magnetic flocculation effect, resulting in shorter chains which are less intertwined, and individual particles have to be recovered. That, of course, is much more difficult than recovering particle aggregates. The result is the overall decrease in our MagSep efficiency as a function of correct medium contamination. Finally, the ultrafine medium particles must also be lost in the MagSep effluent to tails. Studies have shown that it is really the ultrafines in the region of less than 10 micron that is lost to tails. The mechanism here is that larger, more magnetic particles will substitute smaller particles in the magnetic flocculation effects chain until the small particles are eventually kicked out of the chain and report to tails. The bleeding of these ultrafines is necessary for viscosity control, but at the same time, we do not want to lose all the fines because they are also necessary for medium stability. The MagSep in its performance and through the mechanism explained of ultrafine particles being kicked out of the magnetic flocculation chains ensure both viscosity regulation while still allowing medium stability. Finally, a case study on MagSep efficiency. The context of our case study is a ferrosilicon dense medium separation process on a malachite copper ore body. The plant name tag rating was 65 tons per hour head feed into the dense medium separation mixing box. However, with the copper price being really high, the plant was operated at the time at a 90 to 100 ton per hour feed rate into the DMS. The request from the client was for an OEM to investigate the MagSep efficiency, but after a high ferrosilicon consumption was reported at this operation. The table below summarizes for us the design parameters of the particular magnetic separation model that was installed on the site versus the measured operational conditions. Line 1 clearly shows us that the feed rate into this MagSep was more than double the recommended range of the MagSep. Secondly, the recommendation for 0 to 25% non-magnetic solids was also well exceeded by almost factor 3, where there was 70% non-magnetics being fed into the MagSep. The other important parameter which talks to our magnetic flocculation effect, the feed concentration of magnetic solids, was towards the lower end of the recommended range, but still within the range nonetheless. Hopefully, you're already postulating the types of recoveries we can receive by having a MagSep overloaded not only on its feed, but also on the percentage non-magnetic solids in the feed. So without further suspense, the performance results of the MagSep under these operating conditions. The MagSep still achieved a 95.7% ferrosilicon recovery. Remarkably also, 98.2% of the effluent solids was non-magnetic, so very little solids is being lost to tails, and indeed it might only be the bleeding or purging of the ultrafines necessary for viscosity control. However, we could not do PSD analysis on size on these ultrafines, and therefore the particle size distribution in the underflow of the MagSep could unfortunately not be determined. The overdens from the MagSep had remarkably only 4% magnetics in the non-magnetic material in the solids. In other words, we are feeding in 70% non-magnetic solids, but only 4% of the overdens product is non-magnetic. That means that we are effectively purging the non-magnetics from the correct medium, allowing density as well as viscosity control. The overdens from the MagSep dropped slightly from the expected 3.2 to a value of 3.1. MagSeps are the kidney loop lifeline of our dense medium separation process. Our mechanical setup can easily be controlled in the operation, while the process feed conditions are not so easy to regulate and has to play second fiddle to some of the other operational parameters of our entire DMS. Thankfully, Despite grueling feed conditions in our case study, the MagSeps have proved to be resilient in their operation, where they can still facilitate good medium recovery, expected SG overdens, and correct medium density control by purging the non-magnetic solids. Some important points to remember from studies done by the diamond industry is that our overall medium consumption on our DMS is not only a function of the MagSep performance. In fact, they found in their studies that the most important contributor to medium consumption was housekeeping and leaking of correct medium in the plant. If that medium could then, in point number 2, not successfully be recovered back through proper floor and sump design, it ended up with the spillages ending up in the tailings dam. The third important point was the drain and rinse screen operation, where if the medium is not fully washed off of the ore on the rinse screen, that is carried over to either product or tailings and lost. The wet dry magnetic separator was only fourth in line contributor to the overall medium consumption. And finally, they found that the makeup circuit also had some contribution to overall medium losses. It could reasonably be expected, as explained in this presentation, why the MagSep only comes up as the fourth most important parameter, given their resilience and the way that they keep on working despite grueling process conditions in some applications.